I'm going to share my screen, and let me see. We could go ahead and edit this however you like. Okay, this is lesson 7 of the ICED methodology. We're going to talk about rapid concept development. But first, we're going to go back and review a little bit about what you've learned so far in the ICED methodology. We're going to review knowledge construction. We're going to then jump into and also the ICE methodology, but then we're going to jump into a case study to show as an example of what we mean by rapid concept development. And we're going to take the example is going to be the on-orbit repair of the reinforced carbon-carbon wing leading edge, which we had to develop in order for me to fly in space. Okay, so reviewing what we learned in the ICE methodology, how do we learn as a team? How do we construct knowledge? Um, if we see something in the physical world that we don't understand, we try to understand it as best we can by creating a mathematical model. And then we go and we try to duplicate it, what we're seeing by an experiment, in order to evaluate our analysis. And then we go back and forth in the laboratory, varying parameters and testing to failure these ideas. And also we're evaluating our analytical techniques. Once we develop and ensure that our analytical methods for predicting what we see in the laboratory are adequate and can predict failure, then we could use those techniques to basically just analyze, vary the parameters, and look at different designs until we come up with what we call an optimum design, something that meets our needs and is either the lightest weight, the lowest cost, whatever you believe to be optimum. But then after we develop that design, we fabricate that design, we go in the laboratory and we test it. Now, one of the other things you learned in the ICE methodology was we use a building block approach. And this is an example of a cryogenic tank for a reusable space vehicle, right? We look at that tank, but then in order to understand, we look at all the different ways that particular concept can fail. And then we go in the laboratory and we develop small tests in order to validate whether or not those failures will occur, if we understand them, and if we can analyze and design for those ideas. And then we constantly building up those ideas, looking at larger and larger components, intersections of components, so we understand the interfaces. And we can predict how it fails as a larger and larger system until we actually can build and test a full-scale version of our idea in the laboratory. Okay, so that's the building block approach we're going to use. Just to review, this is the ICE methodology. You've been through the process of where you form a team, and as a team, you learn how to capture knowledge. You learn everything about the problem you're going to solve. You dive into it, you immerse yourself in that problem, and then you start collecting information, learning as a team. You're going through a phase called creative concept generation, where you're basically expanding your design space and looking at lots of different ideas. And now we're jumping into the rapid concept development phase, okay, where you're going to jump in and we're going to teach you how to rapidly mature those ideas that you think are the best ideas to solve this problem. Okay, so one of the examples we're going to use is the return to flight, um, and um, and what happened during that. A large, we're going to look at repair of the wing leading edge, and the reason for doing that was that during the launch of STS 107, a large piece of foam hit the wing, caused a problem. And so a large piece of foam hit the vehicle and caused the accident to occur, right? And so we had to go and conduct a large scale test to determine what did that accident look like? What did that damage look like? And what we found out was that a large piece of foam could cause a very large hole in the wing. And so if we were going to fly again safely, we had to understand if we had damage to a wing during the next shuttle mission, how do we repair that wing leading edge? And remember, this is um, um, a very intense area of heating on the vehicle, and it uses a very unique material that was designed to take temperatures over 3,000 degrees Fahrenheit. And this is called reinforced carbon carbon. So what we do is we look at all the different ways we've had damage in the past on space shuttle. You could have coating chips come off as shown here. You could have small cracks in the skin of the vehicle as shown here of the wing leading edge, or you could have a very large hole. Okay. And so if we're going to design something to work, we have to look at all these different cases that we could potentially have when we inspect our vehicle on orbit. So for some reason, it's not showing some of my slides. Okay. So when we looked at this problem, and we looked at it as a team, we started looking at all the different ways you could potentially repair this vehicle, this wing leading edge. We looked at cases where you have just a small crack. Then you might put a putty-like material on the outside. You might use a putty knife to basically smooth it over the surface, special material that bonds to the wing leading edge. You could put a patch over the wing leading edge and secure that patch down by adhesively bonding it, or you could stuff the hole with a repair and cover it with what we're calling a plug. And then you have other concepts to actually repair a very large hole in the wing leading edge, where we might take a large piece of material, drape it over the hole of that wing leading edge, and secure it. So what you're doing with your team is, as you're looking at all these different ideas for solutions to different types of damage, now you're selecting which concept and which category of repair are you going to work on. So in our particular case, we were looking at helping the program develop a plug repair concept. You go through this creative concept development phase, where you're basically looking at exploring all different creative ideas. You sketch those ideas up as you see here for one of our solutions. And our solution for a plug was basically to develop a carbon-carbon flexible doubly curved shell. And that's what you see here. And it's flexible so that we could drill and tap a hole in the carbon-carbon wing. We could develop a carbon-carbon fastener, and we would secure that flexible shell onto the vehicle by basically screwing that fastener onto the wing leading edge, securing it so that you see, even though the wing leading edge is curved, you notice on the figure on the right, when you secure it down, that that shell is so flexible it just flattens right down. And what that's going to do is going to help us to develop solutions that would work in multiple different areas of the wing leading edge where you have different curvatures. Okay, so this was the concept, right? The idea was to drill and tap a hole in the wing leading edge, tap it so that now you could put a carbon-carbon fastener, you could screw it in. That means that fastener would be secured mechanically. Some of the other ideas we thought about were possibly having a low temperature glass gasket that would melt during heating and basically form another bond. When we think about ways to solve this problem, we think about all the ways it could fail. And so let's say the screw mechanism doesn't hold it. Is there another way that would secure it so that we have two different means of securing that patch onto the wing leading edge structure? Okay, this is the advanced carbon-carbon here, and this is the plug here. And you notice how nice and flat it is. You notice that when you heat it, it basically fuses that material together so that it holds it in place nice and tight. That was our idea. We looked at many different options of those ideas. So what you're going to do with your ideas, you're going to look at multiple different concepts, multiple different materials that you might want to use. We looked at the possibility of how this could possibly fail. Maybe the concept as you're pushing it down and flexing it, that curved plug would crack. So we looked at, are there ways to make it thinner and make it more flexible so that it would ease that stress in the component so it wouldn't break. So here we have multiple layers that are very thin. We looked at very thin um, concepts, and then we looked at just single concepts like this. Okay. So as you're developing your category of ideas, you want to look at lots of different options for developing those ideas. And then what you want to do is you want to put together a plan for how you're going to solve this problem. Okay. You look at all the different ways it's going to fail, right? When you have your ideas and all its options, you're looking for all the different ways it's going to fail. And then what you do is you're creating a test plan for you to evaluate all your different ideas simultaneously by going through this process, this test process. So you develop sets of ideas. And so what we did was we laid out a planning and a test and analysis strategy for how we would rapidly develop these concepts. So you look at the different components of the concept. We had the curved shell, we had the gasket development, and we had fastener development. You look at multiple different ideas, multiple different materials. For those gaskets, you might want to use a ceramic material, a composite ceramic material. You might want to use a metallic material because certain portions of the wing might not be as hot and might not need that reinforced carbon-carbon. A metallic material might work. For the gaskets, we looked at ceramic cloths. We looked at ceramic cloths filled with a low temperature glass material that would become liquid and basically bond with the structure and cause that bond of the gasket to the curved shell, to the substructure below. And we looked at different types of fasteners. We looked at metallic fasteners. We looked at ceramic fasteners. Okay. And then what you do is you go through this building block approach of testing these different ideas using different ways to test. And we'll show you how we do that with the filled materials, wicking test for creating the drill bits that we need to drill and tap the holes in the wing leading edge. So now we step through that process. We did this in a friend of mine's laboratory. You could do it at home. He had a laboratory in his garage. And what we did was we started building many different ideas using all different types of materials, maybe not even the actual materials that you would use during the test, but something that could show that or demonstrate the concept. For instance, the concept of having it doubly curved and then pushing down on it and allowing it to flex. Okay. So for the drill bit development, we tested dozens of different drill bits. But one of the problems was drilling through advanced carbon-carbon has a silicon carbide coating. Okay. And drilling through that very hard coating was difficult. So what we did was we developed a technique by experimenting to actually chip the coating away. So what you're going to see in this video is we used a center punch tool to basically chip the coating. And then we developed this tool that actually not only drills, but also taps different size holes depending on what size the hole damage was. You want to drill it out a little bit more and then just put a fastener in there to solve that particular problem. Then the next phase of that, we start looking at developing this tool, and we have an astronaut testing this tool with many different drill bits, many different versions of the drill bits, but he's actually using the actual drill that the astronauts use out in space when they're in the vacuum of space. So we're actually testing the hardware with actual flight hardware that are going to actually operate at the correct torque settings to see if an astronaut could do this on the ground, right? And then we actually flew these in space, and we actually would like to demonstrate that in space. And we also were able to get a patent for this idea because it was a totally new idea. So many of the ideas you come up with will be brand new. Okay. Now, the other thing we had to do was make sure that this plug, once we developed a technique for drilling the hole, we had to make sure that this doubly curved shell would survive the extreme heating conditions up to 3000 degrees Fahrenheit. And so what we did was, since we weren't going to fly it in space, first we wanted to test it in the laboratory. We tested it using an acetylene torch, and we looked at, we had an IR camera, so we knew what temperatures we were testing to. Okay, then we stepped up that idea to better simulate what the actual flow environment would be. This is called an arc jet facility, but it's a very small arc jet facility, so we could test small samples that you see here under flow conditions. Now, one of the things we had to understand was when you put this patch on the outside of the vehicle, the flow hits that patch and it causes heating to be very high. You notice in the upper right in this figure, here's where we had to use what we call computational fluid dynamics analysis that simulates that hypersonic flow. And you notice that on the lip of this patch, you see extremely high heating and high temperatures. So now we had to determine how thin we make our patch and what should be the design parameters so that we wouldn't cause an over temperature, we wouldn't cause our patch to basically burn up in the arc jet. So for this test, we go to a full-scale arc jet facility, very expensive facility at Johnson Space Flight Center, flows coming from the left to the right. And now we're testing our concepts. After we looked at dozens of ideas, we're testing our best ideas in a more realistic environment. So we're stepping up this building block approach from acetylene torch to a small scale arc jet to a very large arc jet facility. Okay. The next thing we wanted to do very simply was understand, can we make flexible plugs out of ceramic composite material that wouldn't crack? And so you could perform very simple tests. You go out there, you have a manufacturer, you got to think of innovative ways to research and get people to manufacture your ideas or build your ideas. And we did that. And so we do these very simple flexure tests. You could design more precise flexure tests with larger and larger specimens with an actual test facility where you could apply a load, you know what a load you're applying, and you're actually measuring the deformations and the stresses in your component. Okay. We wanted to do this so that we could now look at different size patches and how they would fit in on all the different to basically plug and repair damage in all different areas on all the different wing leading edge concepts. Then we go and we build these concepts. We test them on a real uh, version of an RCC panel at multiple different areas. We build the fasteners, we screw them down, and we see how well does it flatten against the surface of the wing. And are our predictions, are we able to simulate those predictions in the laboratory by a test? And then we actually develop the tools to actually insert the plug and to make sure we could secure it down adequately. And we create tools to actually measure the bump to the flow, how thick is it, against the surface of the flow? How flat is it against the surface of the flow? And how secure is that patch? If an astronaut is actually going to put this on the vehicle in space. And then this is a video of me in space demonstrating this inside the cabin of the vehicle. And that's the next step would actually be to have an astronaut outside the vehicle demonstrating this repair technique. So this is another idea we had for the very large area repair. A separate team was working on a flexible sheet of this a reinforced carbon-carbon. And you could see one of the techniques for basically securing this sheet is actually using some of the plug ideas that we had already developed. So we're building an entire toolkit for the astronauts to use for very small damage, basically just putting a fastener inside a very small hole that we drilled out of damaged material, to a larger size plug, to the very large size sheet of material that we could secure down with all these individual plugs. And that basically is the technique you use for addressing and maturing these ideas as quickly as possible. You don't just look at one idea like a metallic concept. You look at multiple sets of ideas simultaneously, running them through this same series of tests, whether it's the bend test, whether it's the aerothermal test where you're actually heating these ideas to understand the limits of where on the vehicle it would survive, or it's the structural test. Okay. And so when you look at all the different ideas that our small team developed, we not only developed the tools for drilling, we developed the fasteners that would fit in those holes that we drilled. We developed a torque limiting tool so you wouldn't over torque the screws as the astronauts were screwing them in, so they wouldn't break in space and cause a problem. We developed fasteners. We developed the flexible plug. We developed the small area repair, and we also developed a large area repair. And we did this in a period of 3 to 6 months. So we did this very rapidly. So when you start looking at your ideas, and uh, Mr. Jim Gorman is going to have you do that, what I'd like to see you do is look at all the different ideas, all the different variations of your ideas, and put together that rapid concept development plan. Think of all the different ways it can fail, and think of all the different series of tests you'd like to perform in order to gain as much knowledge as possible. So when you pick that one idea, you're very confident that that idea will work. Thank you. Okay, any questions? Okay, this is where, James, I'm going to stop the recording.